Hello! It's been a bit. Today we are going to finish talking about the algebra of elliptic curves so that by Thursday this week we will be encrypting and decrypting messages for ourselves online. So my first mini lecture is about addition of points on elliptic curves, and then part 2 will be on multiplication on elliptic curves. So there is a simple rule that governs how to add points on elliptic curve. And the idea is that if you draw a line, that line will intersect your elliptic curve in 3 points, and all 3 of those points are going to add up to the identity. Now this is a little bit easier to see with a picture, so you can click on this link in the slides or just copy it. And here we have an elliptic curve that I've plotted out. So in black here, I've got the curve y squared equals x cubed minus 2x plus 7. And the 2 points in red are both x and y pairs that belong to the curve. So this graph is special because I've set up the sliders. You can pick the coordinates. A will be the x coordinate of this point, B will be the x coordinate of this point, and then the page will just calculate what y coordinate gets you above the x-axis here. So you can slide it around. And notice that no matter where I pick these, the blue line will be the unique line that is drawn between those 2 points, and it always hits the curve in one other spot. So if this was the point P, this is the point Q, I could maybe call this the point R. And the rule would tell me that P plus Q plus R gives me identity. So part of the motivation for this rule is that our whole idea with inverses for elliptic curves is if you have a point P on the elliptic curve, its inverse is the point that has the opposite y coordinates. This would be minus P down here. The vertical line that connects those 2 points, it intersects once at minus P, it intersects the curve again at P, and then it intersects the curve a third time at that point at infinity. And does identity plus P plus minus P equal identity? Yes, it does. We have very enthusiastic geometers in the audience today. So that logic is going to extend to other lines between points. So these 3 points would add up to give the identity. If I move my coordinates, this point P plus this point Q plus this point R will add up to give the identity. So if you actually want to know what P plus Q makes, we're going to use the rule. If you have 2 different points P and Q, step 1, draw a line between them. Step 2, find the point R where the line intersects the elliptic curve. And now step 3 is the tricky bit. Because P plus Q plus R equals identity, it's a little bit of algebra to say P plus Q has to equal minus R, right? So whatever point P plus Q is, it must be the inverse of R, which means that on my graph here, if this is P, and this is Q, and this is R over here where my mouse is, minus R is the point down here with the negative y coordinate from r. So this p plus this q makes minus r, and it'll be down here where my mouse is. And that'll work for any two different points on the elliptic curve. So I can move my sliders around. Let's put A on the left and B on the right there. And let's flip them around a bit. So here's P, here's Q. The third point of intersection, I might have to zoom in a bit to see it there. Here it is where my mouse is. P plus Q plus R makes identity, so P plus Q must make minus R. Minus R is the point that has the same x coordinate as R, but the opposite y coordinate. So this P plus this Q makes this R, right where my mouse is. Now, you might notice as I move these sliders around and I make the points get closer and closer together, something is happening to the line that I've got. If I get closer and closer and closer, it looks like I'm making a tangent, but then if I take these points to be exactly the same, my formula stops working because I'm dividing by 0. So down here in formula 6, you can see I've got this b minus a on my denominator. But as long as we're close to having the same point, it looks like we're having about a tangent line there. So for adding a point to itself, it's a slightly different operation. We're going to use a tangent line. And I'll have to use a different formula there, so a little bit of calculus tells me what the formula for the tangent line is going to be. So here's my elliptic curve again in black. Here is my point P in red. And I want to add the point to itself. So I've dropped in a tangent line in blue. And it intersects the curve in one other place. So for the problem of adding a point to itself, it'll be guaranteed that it'll be guaranteed that your line hits the elliptic curve in one other place. And again, since P plus Q now makes identity, it must be that P plus P makes minus Q, and that'll have coordinates. In this case, it'll be x coordinate 2.031, y coordinate negative 3.364. So down here a ways. So P plus itself will be this point minus Q all the way down here. Now, there are formulas for these forms of addition. You know, I'm not expecting everyone to plot out a graph and do this by hand every single time, and that's not the way that it's done for cryptography purposes anyway. So just as a refresher from, say, Calc 1, the line between two different points, P and Q, all I need is the slope of the line and the coordinates of one of those points, and that's all the ingredients I need to find the formula of that line. So let's say that P has coordinates xy, Q has coordinates x prime, y prime. The slope is going to be the difference of the y's divided by the difference of the x's. And I'll go on and say that the new point, P plus Q, is going to have the following coordinates. The x-coordinate of the point P plus Q is equal to the square of the slope minus both of the x-coordinates from the original P and Q. The y-coordinate of P plus Q will be the slope times x minus x double prime. So this is the x belonging to the point P, and this is the x coordinate belonging to the new point that we just calculated in the previous formula. And then that'll be we'll also subtract y from that. Now, the benefit to having formulas for this, again, so we don't have to use the geometry every single time, or you might think that really geometry and algebra are two different tools for working with similar ideas, right? Graphs and formulas are just telling us different things about these mathematical objects. The very nice thing about this formula is this is something we can just hand off to a computer, but also, as long as we are careful about it, we can use this point addition formula in modular arithmetic instead of with real numbers. And I will explain a bit more on Thursday why that's a sensible thing to do, why that is something that actually works, and we can still say intelligent things about lines and intersection and stuff when we're only talking about modular arithmetic. But also, that's a necessary step. Just like we saw with encryption using modular arithmetic, the security of our crypto system comes from the discrete logarithm being a difficult problem. So we need to make this whole system discrete in order for it to be secure. Again, we'll talk about that more on Thursday. So that's enough for part one. I'll see you in a bit for multiplication on elliptic curves.